So they talk about quadratic equations. Quadratic are specific equations that are x squared. Their degree is a 2. Highest exponent is a 2. But you're going to use some of the same techniques to solve polynomials that you would have for quadratics. The first thing we're going to do is factor by grouping. So solving a polynomial by factoring is one of the methods, even if it's not a quadratic. This polynomial is not a quadratic because the degree is 3. All right? But you would solve it the same exact way. If this said solve this, you can set it equal to 0 and potentially factor. And so if you can factor by grouping, you can do it exactly the way that you would have done it when you had a quadratic, when you had it to degree of 3. So if I wanted to do this particular one, I'm going to group exactly the same way. I'm going to group my first two. I'm going to group my second two. Look at the first group and say, well, what can I take out? I can take out an x squared, and I'm going to be left with 3x minus 1. What can I take out of the second one? I can take out a 9, and I'm going to be left with 3x minus 1. So we have done this factoring before. This is not a quadratic, but it is one that we can do by factoring. So when I have something like this, I'm going to solve. Now here's the thing. We have now introduced imaginary numbers, all right? And so one of the things you have to look for is, normally I would say, okay, well, I can't set this equal to 0. There's a problem. But with this, introducing imaginary numbers a while back with complex numbers, you can do all of your zeros here. You can do all of your factors. And so I can set this guy equal to 0. That's going to be easy. Add 1 and then divide by 3. But then when we set this second one equal to 0, subtract 9. This is where normally you would say we have a problem. But what am I going to do? Well, I'm just going to do the square root like I would. The square root of 9 is normally 3. When I have a variable involved, I need to say positive or negative 3. But it was a negative 9, so what else do I need to put there? I. Yeah, I need to put an I there, all right? So now I technically have 3 answers here. I have that x could equal 1/3, x could equal 3i, x could equal negative 3i. You can list it with a plus minus in front of it, but I want to point out that there are 3 answers. There are 3 answers here. That we had 3. So this was actually my answer here. 1/3, positive 3i, and negative 3i. There are times when you potentially could have something like this that's not. And so even if I were to get this equal to 0, so if I were to move both of these over, right, and get x cubed minus 5x plus 2, we have a little situation. I can't factor by grouping, right? And I also don't have factors of 2 that add up to 5. So we have a little problem here. We also can't use the quadratic formula because by its name, it works for quadratics. And this is not a quadratic. Quadratics have a degree of 2, okay? And so this method is where I usually would say, okay, one of your zeros is this. So if we were to do like from our quiz, we do factors of 2, that's positive and negative 2. Factors of what's here, positive and negative 1. And I'm going to say, well, it's going to be either positive or negative 2 or positive or negative 1. And I can use my synthetic division to figure out if it's a 0. And then you would be able to factor a quadratic. In this case, though, if you look here, they give us what one of them is. They're going to say one of the zeros is going to be a 2. So we're just going to use a 2, just like we do with our synthetic. X cubed is 1. I do not have an x squared. I need to put a 0. X is 5, and then my constant is 2. And so if we do this whole thing out, right, we have this guy. So I know that if that's my factor, that's one of my zeros. Typically, they'll give it to you. They'll say this is a 0, right? So this is one of my factors. And then I'm down here, and I'm going to just go down 1 from where I started. So 1x squared plus 2x minus 1 equals 0. This is a quadratic, all right? I'm now at a quadratic point. So my first thing that I do when I have a quadratic is, can I factor it? So I'm like, well, factors of 1, positive and negative 1, potentially, but in this case, negative 1, that will add up or subtract to give me 2. If this were a positive 1, I could say positive 1 and positive 1 go to 2. But this is a negative 1, so I know 1 has to be positive and 1 has to be negative. This is not going to work, right? So I can't factor this. There's no way to factor it. There's no way to get, that's the only way to get a negative 1 at the end. And that's not going to give me a positive 2 in the center. So if it's not factorable, my next step is to say it's a quadratic. I can use the quadratic formula. So here I can use the quadratic formula. I couldn't do it to begin with because it wasn't a quadratic. All right? So at this point, I can use the quadratic formula. What is the quadratic formula? So I need to know the quadratic formula to be able to use it. At this point, I can use the quadratic formula, all right? And it's small numbers, so they're nice to us. Negative b, that's my b right there. So I have a negative 2 plus or minus the square root of 2 squared minus 4 times a, which is 1, times c, which is negative 1, all over 2 times a, which is 1. All right. So when I do all of this, I have a negative 2 right here, and I'm just simplifying that piece of it. So I'm just simplifying that negative 2 squared, that piece right there. Negative 2 plus or minus. On the inside here, I have 4, and it's minus a negative 4, right? 4 minus a negative 4 looks like that. All right. When you have that, you're going to continue to simplify. So I'm going to simplify over here. Negative 2 plus or minus the square root of 8 over 2. Here's where you have to do your factor tree because 8 is actually simplified. It can be simplified, remember? 8, we have 2 and 4. 2 and 2, if it pairs up, it comes out. If it doesn't, it stays in. Okay? So when I do this, I have negative 2 plus or minus 2 square root of 2 over 2. All right? You can reduce anything on the outside if they all reduce. All right? Which means I have 2, 2, and 2 on the outside. As long as something comes out of all 3 of those, I can reduce it. I cannot reduce with the inside, only outsides can reduce. So clearly, 2 comes out of all of those, right? So I can say 2 divided by 2 is 1, 2 divided by 2 is 1, 2 divided by 2 is 1. And so while my first answer they gave me, they said, hey, 2 is a 0, if I'm looking for my zeros. They gave me this one, so I know that's one of them. And then I have this guy that I just reduced, and you can leave it 1 plus or minus the square root of 2. Technically -1 there, because I still had a negative. So there are going to be times when you can factor, like we did on the first one, right? Or there are going to be times when you cannot factor. If it is not factorable, you can use quadratic formula. And by the way, you can always use the quadratic formula, even if you don't know how to factor it. Even if it's factorable, the quadratic formula will work. You'll just get whole numbers or integers there, potentially, if it's factorable. Theorems here. To the right of that, we have a picture of mathematician Gauss. He's the first person to prove this theorem. The fundamental theorem of algebra says that every polynomial equation of positive degree n has at least one complex root. Complex meaning real, imaginary, or a combination of the two. The corollary of that is every polynomial equation of positive degree n has exactly n complex roots. All right? What does that mean? Well, let's look back at what we've done. So this one right here has a degree of 3. When we solved it, how many zeros did we get? Well, let's look back. When we solved it, right? And so when we look, these were my zeros. I have a degree of 3, and I had 1, 2, 3 zeros. All right? That's what this is saying right here. That whatever your degree is, remember your degree is your highest exponent, then you will have exactly that number of zeros. Even if some of them are imaginary, or even if some of them are square roots, you will have exactly that many, or even if they repeat. So you could have x minus 1, x minus 1 as your factors, and technically 1 happens twice. Even if they repeat, you're going to have exactly that many. So whatever your degree is, you're going to find exactly that number as your answer, all right? And if state the number of complex roots, that's an easy question. When it says state the number of complex roots, you literally just have to look at the degree. The number of complex roots that this is going to have is going to be 4. That's all you have to answer. When it says, what are the number of complex roots that this will have? You look at the degree, which is your highest exponent, and you say it's going to have 4. That's how many it's going to have. And the way you solve it are maybe different methods. You may be given one of your zeros, and you may have to do synthetic division to solve, right? It may be a quadratic that you can factor or use your quadratic formula. But it will always go back to that degree. That's how many you should be finding, even if it's imaginary or if it's square root of something. All right, so this is kind of something that you're leading up to as you're seeing these happen. It says irrational root theorem. If a plus the square root of b is a root of a function, that's what p of x is, and square root of b is irrational, meaning something like that doesn't automatically simplify. So square root of 2 is irrational, but square root of 4 is not, okay? Square root of 2 is irrational because 2 does not have a perfect root. But square root of 9 is a rational number because you can actually take the square root of 9, it's 3, okay? So that's what that means. So let's say your square root is irrational. You cannot simplify it out. Then the conjugate, remember what the conjugate means. The negative of that is also going to be a root. Why is that true? Well, remember when we did the square roots over here. If I were to say, well, x squared equals 3, what would my answer be? Well, yeah, plus or minus, because that's how you have to do it when you have something involved. Your answers here would be positive square root of 3 or negative square root of 3. All right? That's what this is saying. If you have an irrational root, you also have its pair that goes with it because it came from the square root of something, which means you had 2 to begin with. And when you have 2 to begin with that deals with a variable, you have to consider the positive root and the negative root. Whereas a square root of 9 potentially didn't come, 3 potentially came from something else. It came from another factor. But square root of 2 had to come from taking the square root of something, which means it has to have a pair that goes with it. The same is true of complex roots. Let's look at this. When you have an imaginary root, it will also have a little partner that goes with it, even if they don't tell you. So if I have something like 3i, then I have to have negative 3i as a root as well. Why? Well, that came from the square root of -1. It had to, okay? And so what had to have happened here is that we had to have something like that, which means I had to consider the positive root and the negative root, okay? So anytime you're given zeros and they say, hey, find the polynomial, and they give you either a irrational or a complex and imaginary, you have to assume that its partner comes with it, all right? They always pair up. Irrational and imaginary roots always pair up when you're talking about polynomials, all right? And so sometimes they'll give you something like this. 2 minus the square root of 3i, or 3, 6i, and -5 plus 7i are roots of a polynomial. What other roots must they have? Well, if we have this, then we have to have the conjugate. What's the conjugate? Just change the inside sign. So I have 2 minus the square root of 3, then I must have 2 plus the square root of 3 as a root. All right, so that's one of the answers. They gave me -5 plus 7i and 6i. So if I have 6i, I have to have the opposite of that, which is -6i. All right, and if they gave me -5 plus 7i, then I have to have the conjugate of that, -5 minus 7i. So these must be roots as well if they gave me these. That's all that's saying. They always pair up. Irrationals and imaginaries always pair up. Okay? So how does that help us? So the imaginary, you should have had the opposite of that one. The irrational, you should have had the conjugate of that one. Why did we not do the -8? The -8 is not irrational, and it is not an imaginary number. So it does not automatically pair up. All right, so the -8 does not tell you anything about another root, but the other two do. All right, and so look at example 5. It says, write a polynomial of least degree with 2 and 5 square root of 3 as zeros. So it wants us to write a polynomial. Write a polynomial of least degree. So the first thing we need to think about is, what's the degree going to be? Well, they've given me a 0 here. So one of my zeros is going to be a 2. They've given me this guy. So another 0 is going to be 5 square root of 3. But that one is irrational. So what do I need to assume? Well, I'm going to have one more 0 that's going to be -5 square root of 3. All right? Does everybody see that? Okay? Now, so that means my polynomial will have a degree of 3. I'm going to have an x cubed when I'm completely done with it. How do I find it? Well, I have to figure out what my zeros are. If my zeros are these, I can just set x equal to those and then get it to 0 for my binomial. So x is going to equal 2, x is going to equal 5 square root of 3, and x is going to equal -5 square root of 3 when the polynomial equals 0. How do I get that into parentheses? Well, I just move it over. So if I move this one over, then I will get x minus 2 is going to be one of my factors. Move that over. X minus 5 square root of 3 is going to be one of my factors. And move that over. X plus 5 square root of 3 is going to be one of my factors. Okay? You'll notice that it's the exact opposite of what's there. Remember, that's how we did synthetic division too, right? So when you are putting it back into the binomial, it also changed signs. So 2 is when it's out of the binomial. We've already solved for it. If I need to figure out what the parentheses look like, I'm going to just do the opposite. So this was a positive 2, this is minus 2. Positive 5 square root of 3 minus 5 square root of 3. Negative is a plus, all right? It wants me to give the polynomial. So we've been going from polynomial to factors. Now we're going to go from factors to polynomials, which means all you have to do is FOIL, all right? So it's easier than factoring because you actually have it in front of you. Let me tell you this though, it's always easiest to foil my conjugates, all right? It's always easiest to foil my conjugates. Here's why. All right, let's talk about conjugates. All right, a conjugate is when you have two of the same thing, but the middle sign is just different. That foiling should look very familiar, all right? A plus B, A minus B always foils to be a special thing. It always foils to be A squared minus B squared, all right? If you'll remember, if I were to foil this out, all right, A and A, that's A squared. A and negative B, that's negative AB. B and A, that's positive AB. B and negative B, that's negative B squared. These two terms cancel. You're left with just the first one squared minus the second one squared, always. So anytime you have imaginary roots or irrational roots, foil those first because they'll always end up being the first one squared minus the second one squared. So this one, while he looks intimidating, it actually foils the easiest here, okay? So I'm going to say this one is going to be the first one squared. That's just going to be the first one squared minus the second one squared. All right? That's how this guy is going to foil. All right? The hardest part of this is just squaring it. All right? So we haven't done anything to the first group. X minus 2 has stayed the same. Let's look at what happens here. Well, x, when I square it, that's just x squared. That's easy. What happens when I square this? All right? I have to square the 5. And I have to square the square root of 3. All right? 5 squared, well, that's just 25. What happens when I square a square root? The root just goes away, so I just have a 3. So I end up having the 5 squared times what's inside the radical, 25 times 3. So this is x minus 75. All right, x squared minus 75. The first one squared minus the second one squared. All right? I'm still not done because it wants me to do the whole polynomial. So now I just need to do regular foiling here. Regular foiling. X times x squared is x cubed. X times negative 75x. Negative 2 times x squared, negative 2x squared. And negative 2 times negative 75 is a positive 150. All right? I need to put it in standard form and I'm done. Standard form is highest exponent to lowest exponent. This is my highest exponent, x cubed. This is my next one, minus 2x squared. This is my next one, minus 75x. And this is my last, 150. All right? What does that tell me? Well, if I were to factor this and find all of the zeros, my zeros would be 2, 5 squared root of 3, and negative 5 squared root of 3. We just worked the other direction. They gave me the zeros, and I had to find the polynomial. Versus what we've been doing, given the polynomial, find the zeros. We're working the other direction. They've handed us the zeros, and we're just working to find the actual polynomial. All right, so I want you to try one. They've given us the zeros of negative 2 and 5i. Figure out what all your zeros are, and then figure out what the polynomial is. So if these are the given zeros, -2 and 5i, then your zeros for the entire thing are going to be -2, +5i, and -5i, which means your factors are going to be what happens when you put those in binomials. It's going to be x plus 2, x minus 5i, x plus 5i. Then you find the polynomial by just foiling. We're just multiplying. I did these first. Remember, it's conjugates, so it's going to be the first one squared. That's just x squared. The second one squared, 25i squared. I can simplify 25i squared, right? So -25 times I squared is +25, all right? Which, by the way, you'll notice is always going to be the square of this guy added, all right, when it's an I. Now that I have two of these, two binomials, I can just do my standard foiling to find it. X times x squared is x cubed. X times 25 is 25x. 2 times x squared is 2x squared. 2 times 25 is 50. And then you need to put it in standard form, highest to lowest exponent. So if I have these zeros, this is the polynomial that it would produce. Meaning, if I were given this polynomial and had to find my zeros by factoring or synthetic division, I would have come up with these. All right?